So this video should not take too long to put together. Let's take a look. So in Unit 5, one of your terms listed is how do we know how much the mass of a galaxy weighs? So there's 1, 2, 3. These are the 3 ways we know how much a galaxy weighs. And the reason we care about knowing how much a galaxy weighs is that there is mass apparently associated with galaxies that is not visible. So of course that gets us to the dark part. So there's dark matter associated with all galaxies. So anyway, here's the ways. One is their dance, the motions of the galaxies, that the motion the galaxies have together as they interact. We can backtrack and know what the mass of the galaxies are. The other is, to me, a little elusive. This is this kind of blue thing down here. We can actually gauge or understand the temperature associated with a galaxy, and then by that know its mass. And then the third one is, to me, not nearly as elusive. We've talked about gravitational lensing. If a galaxy or a cluster of galaxies, if they bend the light of a more distant galaxy, it's called gravitational lensing, and based upon how much they bend the light, then we can go back and understand its mass. So those are the 3 ways. The other thing is on your, I think this might be vocab questions, I'm not sure, but don't quote me on that. So we said with regard to dark matter, it might be ordinary matter, and actually this falls into what we call machos, is ordinary matter. Macho stands for massive, compact, halo objects. So compact means very dense. Halo means where it's located relative, in this case, to a galaxy in the halo region. So machos. So this would be ordinary baryonic material. The other one is a subatomic particle that we're still searching for, some sort of exotic particle that's not an electron, not a proton, not a neutron, something even cooler than that, that actually is everywhere. And so the fact that we have a hard time finding it, it is weakly interacting. Okay, so these are WIMPs, weakly interacting massive particles. So those 2 things with regard to what dark matter might be, and kind of know what machos and WIMPs are. Then we're on to part 2. Part 2, the first term there says something about the major eras in the formation of our universe. So I would probably on my note card jot down these things in bold. I can't remember which era. Maybe I'm going to pick on Planck era. That's kind of the question mark over here. Gut era. These are by forces. Electroweak era. Then we have the eras aren't by particles, but they are by particles, but not forces. So we have the particle era, the era of nucleosynthesis. That's a fun one, right? Little pieces of nuclei are going to be formed. The era of nuclei, where the middle of atoms are formed, and the era of atoms. Of course, I get real excited about the era of atoms because electrons, it's cooled down enough so that electrons can be associated with nuclei, and so they get out of the way, so actually energy can be released. So remember that happened about 380,000 years after the Big Bang. And now, of course, we're in the era of galaxies. So I'd probably put that on my note card. Then there is this, I think from the slide, there's just a question about when did the universe become transparent after the Big Bang? And again, it's the era of atoms where the electrons finally associate with nuclei, and they get out of the way of energy, so radiation, so we can actually see what's going on. So 380,000 years after the Big Bang. Then there's a question about Olber's paradox. So just remember that this kind of thought exercise says, well, we would expect that actually when we're turned away from the sun, that the skies are still going to be bright if the universe is infinite and if the universe never changes. Again, think of this as stars living lives, then dying, and then actually remember, after stars die, they give their material back so new stars can be born. If the universe wasn't changing, everything would be bright everywhere, and if the universe was everywhere the same, okay, but it's not. So in other words, the way this Olber's paradox goes is, since we don't see stars everywhere, then we must, therefore, the universe must have a finite instead of infinite number of stars, and that the universe does indeed change over time. Again, kind of consider this as stars, they have life cycles. Okay, so that's Olber's paradox.